All right. We're going to do the second one together, but I went ahead and put up the answer to the first one on here for you because a good chunk of this is review. So got our exponential function. The first thing I did was name the transformations, which actually that's back from section like 2.7. We did those this semester with that big chart with the A, B, C, D in it if you need to review that. So the negative out front is a reflection over the x-axis. The 1/2 in the front does our vertical shrink. The -2 in the exponent that's inside the function moves it to the right 2. And then the +2 at the end moves it up 2. You should have probably at least had the values -2 to 2 in your table. You can just use your calculator when you plug those in, get the y's to go with them. But I extended a little bit more because all those values were pretty close together, so I didn't feel like that gave me a very good curve. So I gave it a few more places, and that gives me a few more points to the right, and you can see that curve shape happening a little bit more. What you guys should see happening in this table is on one side of the table, you're approaching a certain number for your y's, and on the other side of the table, they're getting further and further apart. So here you can see my values are approaching 2, so it's kind of giving you a clue to a horizontal asymptote. The horizontal asymptote also, in most cases, unless something's weird, is that number that's added on at the end of your function. So that +2 has shifted up 2, which takes our asymptote at 0 up to 2. That's why that changes. So you can always look there if you're not sure what the asymptote is, because you want to make sure when you get to the graph you don't cross it. Domain of these is always all real numbers, which is why we can plug in anything we want for x. We don't have any domain restrictions, any denominators, any square roots. My range here is -infinity up to the horizontal asymptote at 2. Because it's an asymptote, we're going to put parentheses there, not a bracket. And then make sure for your asymptote you have y equals in front of it. It's always a horizontal line that we're looking at for those. Okay. And then, of course, if you have your graphing calculator, you can check that picture. Any questions on that? Graph of the exponential. How'd you do on that one? You're good? Okay. Then the one below it, we're going to go through together just to practice those ones. You're going to see a few of those on Math Excel. All right. Everybody have what they need off of this slide? Okay. All right, so let's look at this one. It says, find the function of the form f of x equals c times a to the x, containing the points 1, -3, 3, -1/3, and then once we have the equation, we'll evaluate f of -2 at the end. When you do these in Math Excel, there might be a couple different forms you're looking at. Whatever you're given, you just need to solve for everything except x and y. So in here, we're looking for c and a is what we're trying to solve for. And all you can do when you have 2 points is plug those points in. So I'm going to do this twice. I'm going to plug in 1, -3. -3 is my y, or f of x. 1 is my x. So it's going to look like -3 equals c times a to the first. And then if I plug in 3, -1/3, it's going to be very similar. -1/3 equals c times a to the third. So what I've created now is a system of equations. So we've got 2 equations that have the same 2 variables. Now, this is not a good set to use with elimination, solving with elimination, because you'd have to add and subtract the equations, get a variable to cancel. That's not going to happen here because we don't have a linear function. So you have to solve with substitution, which means in one of the equations, you want to get one variable alone. It's probably easier for that one on the left to get one of the variables alone, either c or a, because remember, anything to the first power is just that number. And then again, you can get c or a alone. Let's say I want to get c alone. C is equal to -3 over a. Okay. Once you have a variable alone, you can plug that in to the other equation and do that substitution. Hello, come on in. You're good. All right, so we're going to replace c with -3 over a. So I have -3 over a times a to the third power. You can multiply those together if you want. Oops, don't do that. There we go. -1/3 equals -3a to the third over a. And then what happens with those a's on the right side if I have a to the third on top and an a on the bottom? One a is going to cancel. So I'm going to have -1/3 equals -3a squared. And now you can solve for a. How do I solve for a? Divide by -3. It might be easier to think of it as multiplying by -1/3. Multiply by the reciprocal, because dividing by a fraction by something can get a little messy. So if I multiply by -1/3, I would get 1/9. And then we take the square root. When you have the square root of fraction, it's just square root of the numerator, square root of the denominator. So square root of 1 gives me 1. Square root of 9 gives me 3. And then we don't have to worry about plus or minus here, because if it's an exponential function, the base, a, that's taken to the power, must always be positive. It's part of the definition of an exponential function. You're never going to have a negative base. So 1/3 is your base, your a. Once you have a, you can plug it back into that other equation to get c. So you do -3 divided by 1/3. Dividing by 1/3 is the same as multiplying by 3, so you're going to get c is -9. So then your final answer, f of x equals my c -9, my a 1/3 to the x power. That's my function. And then you could always double check before you do anything else with this, that the points that you have work. Plug in 1, make sure you get out -3, plug in 3, make sure you get out -1/3. Second part of the question said evaluate f of -2 now. So that's -9 times 1/3 to the -2. -2 power means flip it, make it a 3, and square it. So that's 9 times -9 gives me -81, should be your answer for that second part. Okay. All right, what questions do you have on that problem? Finding the equation. This is probably one of the more difficult ones you would see like this, where you don't have a 0. Zeros make it easier because you get a variable to go away pretty quickly. This one also was kind of messy with the fractions. Okay, good. All right, so we're going to finish up 4.1 today. You don't need the big idea worksheet today. The back of your big idea worksheet is for 4.2, so just hang on to that. We are going today to practice some of our old formulas. Most of these are. Do you guys remember using interest formulas, simple interest, compound interest, exponential equations for real life problems? We're going to see all those today. So hopefully a good chunk of this, especially the interest stuff, is going to be reviewed for you. So first formula you need to write down, and with each formula you should at minimum be writing down what the variables stand for. In this formula, I is our interest that we're calculating. P is principal. Principal means your deposit amount, what you start with. T is going to be our time, and in all of our interest problems, the time is measured in years. R is our interest rate, and it will be a decimal when you put it in. Okay. And again, this calculates I, our simple interest. Simple interest means we are only earning money from the initial amount you put in the bank. So if you have $100 in the bank, you will only ever earn interest on that $100. That's it. So example problem, it says find the total amount in the bank, assuming that $10,000 is deposited at a simple interest rate of 7.5% for 2 years. So you should be able to pull out the important information, what each variable stands for, and then really these are just plugging it in the formula and simplifying using your calculator. When we round on to problems like this, how many decimal places do you think we're going to round to? 2 decimal places, because dollars and cents, always, okay? All right, so the first one says find the total amount in the bank, assuming $10,000 is deposited. So what is $10,000? What variable? The principal, P, at an interest rate of 7.5%. So 7.5% as a decimal. First of all, I'm going to move that decimal 2 spaces to the left, 0.075. And what variable is it going to stand for? R. And then 2 years is going to be my time, T. Plug it in. I equals PRT, 10,000, 0.075 times 2. All right, now I'm going to calculate. I get 1,500. is the interest after 2 years. Does that answer the question? What's the question asking for? Total amount in the bank. So $1,500 is the money we earned on our interest, but we also had that initial deposit of $10,000. So we're going to add on the $10,000. Our final answer is going to be $11,500. That's it. Any questions on simple interest? No? All good? Okay. Let's do a problem with compound interest. So formula, again, you should probably recognize this. Lot of the same variables here. P is still principal, R is still your interest rate as a decimal, T is still time in years. A is our total amount after that many years, and then N is the new guy. N is going to be the number of times your interest is compounded each year. All right, so what does compounding mean? So let's go back to that $100 example. Let's say I have $100 in the bank and I earn 5% interest. So after a year, simple interest, I have $105. If we compound annually, one time a year, at the end of that year, instead of my interest being calculated on the original 100, I would get money based on the 105 total that's in the bank. So we're earning interest on our initial deposit, and we're also earning interest on our previously earned interest. So instead of earning interest on 100, I earn interest on 105, which means I get a little more money year 2 rather than what I got on year 1. And the more times you compound, the more often that interest is thrown back into the deposit, so the more money you make. The more you compound, the more money you make. All right, so common ways that you can compound money are listed below here. Annually, if something happens annually, how many times a year is that? 1. If something happens semi-annually, how many times a year is that? 2. Quarterly, monthly, and daily. Yeah, and we're not going to worry about the extra quarter year. We'll just say 365. So those are all the N values that you're going to use in the formula. So you're going to look for these keywords when you get to your interest formulas. If you see annually, N is 1. If you see quarterly, N is 4. So we're going to do an example at the bottom here. It says, assume that $5,000 is deposited at a 6.5% interest rate. We're going to find the value of A, the total amount in the account, after 1 year. If the interest is compounded, we'll do it semi-annually first, and then we'll compare that to monthly second. What is $5,000? What variable? 5,000 is P. 6.5% is what variable? R, and if I put that as a decimal, it's 0.065. 1 year is my T, and then semi-annually and monthly are going to give me my N's. So semi-annually, N will be 2. Monthly, N will be 12. That's going to be the only difference between part A and part B. And knowing what you know about compound interest, which one's going to be bigger, semi-annually or monthly? Monthly is going to be bigger. The more times you compound, the more money you're going to make. All right, so let's look at semi-annually. Let's plug it in the formula. A equals my P, 5,000, 1 plus my interest rate, 0.065, over my N is 2, and then in my exponent, 2 times 1, or 1 is the number of years. And then you just type it in your calculator, and your graphing calculators, you guys can do this all in one step. So no need to worry about rounding or anything until the very end. And you should get $5,330.28. So double check that you can get that number okay. Monthly, same thing, just change your N to 12 in your formula. Type it in, see what you get. $5,334.86 if you round to the nearest penny. Okay. Everybody getting that okay in their calculator? Did you guys try it? Okay, so that's simple interest and compound interest. Any questions on compound interest using that formula? These are going to be pretty straightforward. Just find your variables, plug them in. All right, the third formula for the day is the last type of compound interest. So if you guys start making n bigger and bigger, we won't always get more money. It's not like our money is going to go to infinity. It kind of starts to level out almost like an asymptote because it's an exponential function. And if we make n close to infinity, a very large number, instead of using our compound interest formula, we can use a continuous compound interest formula. So you're going to see the word continuous. That's going to be the key word in these problems. It is compounded continuously. Think of that as an n value that's getting close to infinity. It's approaching infinity. We use this formula here. Have you guys used E in science before? That number 2.718-ish? No? Okay. It's like pi. It's an irrational number. It goes on forever. It shows up in a lot of scientific formulas. It's called Euler's number. It's a button on your calculator. It's above the division key on your calculator. You guys can see the E. So nothing you're ever going to have to plug in for E. You just use that value, that 2.718. So if you see that something's compounded continuously, we use the PERT formula, we call it for short. All our variables stand for the same things here. P is still principal, R is still interest rate, T is still time. So example at the bottom, it says, find the amount when a principal of $9,000 is invested at a 6% annual interest rate, compounded continuously. Those are the keywords we're looking for if it's going to be using the PERT formula for 6 years and 9 months. Again, it's just a matter of find your variables, plug it in, simplify. What is P? 9,000. E is always just E. What's R? 0.06. And then you got to be careful with the years on this one. So 6 years and 9 months. You have to think about 9 months is what fraction of a year. So how many months are in a year? 12. So we have 9 out of 12 months. So 9 over 12, think of that fraction. What does it reduce to? 3/4 as a decimal is 0.75. So I have 6 3/4 years or 6.75 years. And then type it in. Again, the E button is above the division key that you're looking for there. Two decimal places to the nearest penny, 13,493.73. So think of that as like the maximum amount of money that you can have at the end of that time period at that interest rate. All right. Any questions on compounding continuously? All right, great. Nothing you need to write down here. I just want to make a note of it to you guys. So like the graphing problem we did on the big idea worksheet, some of your graphing problems in Math Excel might not have a number that's a base. Well, they all have a number that's a base. I take that back. Might not look like a number. It might look like an E as a base instead. But I want you to know it is the exact same as any other exponential function. E is just kind of a gross number for the base, but it's a number bigger than 1, so it represents exponential growth. So all of those properties that you guys learned about yesterday, as far as like domain and range and asymptotes and transformations, if it's a base of E, they are exactly the same. Okay? You just will get some gross numbers when you plug in your numbers in your table because you have a base of E and not a nice pretty integer down there. Okay, but if it's a base of E, everything is exactly the same, and those will pop up a little bit on Math Excel. I think there's like 1 or 2 of those, so I just wanted to mention that. All right, last 2 formulas that we need are, now we're going to kind of step away from our bank situations and just talk about general exponential growth and decay in other real life situations. First formula you need is here. Now this formula actually is very similar to the PERT formula if you look at the form of the equation here. So instead of a P, we have an A sub 0. It still means our starting amount. It just is out of the context of that banking world, and it just could be a starting amount or initial deposit of something else. We still have E. Instead of an R, we have a K. K is your rate of growth. And depending on if you're growing or decaying, K could be either a positive or a negative number. So if you're going to have exponential growth, K will be a positive decimal. If it's decaying, K will be a negative decimal. So for example, if I'm growing by 5%, K is 0.05. If I'm decaying by 5%, K is negative 0.05. You just put a negative in front of the number. And then T is still time. It just might be a different interval of time. It might not be years. It might be like minutes or half lives or something like that. If you're not sure whether to use this formula or the other one that we're going to talk about in a second, look for this key phrase. This formula models if there is a constant rate of increase or decrease. If we are constantly increasing, think about that continuously compounding, those words will be in the problem with these, okay? So look for that little phrase if you're not sure which formula to use. So this example, it's kind of a two-parter. It says in 2008, the median price of a house in Miami was $190,000. Assuming a rate of increase of 3% a year, what can we expect the price of the house to be in 2013? So again, keywords here, rate of increase. If it's exponential, guys, you will be increasing by a percentage. It might even say like doubling or tripling, right? That's like 200%, 300%, but exponential is a percentage versus like if linear functions, y equals mx plus b, that was just a constant amount that we were going up or down by. So as soon as you see that percent there, that screams, hey, it's exponential. Rate of increase tells me I can use this formula. P is the starting amount. In this problem, it's the initial value of the home, which would be 190,000. E is always just E. It is increasing by 3%, so my K is 0.03 because it's increasing, it's a positive 0.03. And then the only other thing I'm missing is the time. It started in 2008. We're looking for 2013, so how much time has gone by? 5 years times 5. And then you type it in. This is still a money situation, so we'd probably still round to 2 decimal places. Unless it said otherwise. $220,748.51. Okay. So we're increasing. We get a number bigger than what we started with. Second part of this problem, we're going to be doing the same thing, but now we're going to be depreciating or decreasing by 3% a year. So this time, we should expect a number smaller than 190,000 if the price of the home is going down. What's going to change in my formula? How's it going to be different, Steven?
You just add a negative in front of the
That's it. You just put a negative, and that negative exponent's going to make it smaller. 190 E negative 0.03 times 5. I get 163,534.52. Okay. Good. Questions? All right. All right, so last slide is the formula that you guys probably used in Algebra 2 when you did exponential functions, probably even Algebra 1, some of you might have done this in. Do you guys recognize y equals a times b to the x? Does that sound familiar? This was in the video yesterday too, I think, with the graphing. If b is bigger than 1, if b is between 0 and 1, let me write that down actually. If b was bigger than 1, it represents growth. It's your growth factor. If b is between 0 and 1, it represents decay. A is your starting amount here still, that number out front, and then X still will be some sort of time, but again, it doesn't have to necessarily be years anymore. If you're not sure to use this formula or the previous one, if something is increasing or decreasing by a percent of its current value, that's when we use this formula. By a percent of its current value. So this time, instead of constantly increasing, instead just every time unit it jumps. Okay, so think of it like a scatter plot versus a continuous line would be the difference. Every certain time period it jumps to the next value. So example, each minute a culture of bacteria increases by 5% of its current amount. If there were originally 25 bacteria in the jar, how many will there be after 1.5 hours? So you need to find A, your initial amount, B, your growth rate, and then X, your time, are the 3 pieces of information we're looking for here. What starting amount do we have? How many bacteria? 25. Now be careful with the growth rate. I will tell you 99% of the time when people make a mistake, it's in the growth rate. If it's growing, which it is here, it needs to be a number bigger than 1. So what number am I going to put here to increase something by 5%? What number can I use? 1.05. What if it's a decreasing by 5%? What number would I use? 0.95. Think of it like 100% is your starting amount. If you're increasing by a percentage, you add it to 100%. So we have 105% in this case. Or if you're going down by a percentage, you're going to subtract it from 100%, which is where we're getting 0.95 from. 95% is 5% less than what we started with. Okay, so always think about 1 or 100% as your starting amount, and you're either adding to 1 or taking away from 1 if you're growing or decaying. And then be careful with the time on this one. It says each minute is when it's going to increase by 5%, and they said 1.5 hours have gone by. So what's my X going to be? Yeah, you've got to convert that to minutes, 90. And type it in. And then because this is bacteria, we're just going to round to the nearest bacteria, I guess. We can't have like partial bacteria. Oh, I typed that in wrong. Let's try that again. 2018. So round to the nearest integer, bacteria. Okay. All right, so I think that covers all of our exponential formulas that you need. Simple interest, which isn't really even exponential, compound interest, compounded continuously, and then the 2 different ways you can model an exponential growth or decay function. That'll wrap up section 4.1. Okay, questions for me? All right, so 4.1 Math Excel is due on Sunday night, and then 4.2 is going to be due on Tuesday night. So those are going to be your last 2 Math Excels before break. Tuesday in class, we're going to be doing an open note quiz. It will be individual, but open note over these 2 sections, 4.1 and 4.2. So just kind of be thinking ahead to that happening on Tuesday.